Now we will see first entropy and unavailable energy. Okay, how entropy is equated to unavailable energy we will see now. Okay, now in a heat engine, the engine absorbs Q1 amount of heat from a source at high temperature T1. It does some W amount of work and rejects some Q2 amount of heat into a sink at lower temperature. Okay. Now, before performing this cycle of operations, right, what is the available energy? Means, because the source is at temperature T1, I know that I can take Q1 amount of heat, right, to convert it into work. Of course, I cannot convert all Q1 because second law forbids that. But before performing the cycle, I know that Q1 amount of heat is available for me to convert, right, into energy. So I am taking Q1, I'll convert some amount and reject this Q2. If I do one more cycle, what should I do? Again, I'll take some Q1 amount of heat from the source. Again, I'll do some W amount of work. Again, I'll reject, right, some heat Q2 into the sink at lower temperature. Okay. Now, what about this heat which is getting rejected into the sink at lower temperature? Okay. That cannot be converted into energy because every time I do one cycle of heat engine operation, every time I'm taking heat from the source only, I'm rejecting some Q2 amount of heat into the sink at lower temperatures. Means, right? So in the next cycle also, any number of cycles I do, I'll always keep on taking heat from source only. But what is happening to the heat rejected into the sink? That is becoming unavailable for me to convert it into work. Okay. No, sir, we have to convert this energy also into work. Means there is one more option for me. What should I do? I have to make this sink as source for another heat engine. Okay. Find out a lower temperature than T2. Then operate that heat engine between the T2 and still lower temperature, some say T3. Okay, so there will be another heat engine, okay, right, where this sink becomes our source, right, and there is another sink at still lower temperature T3. That is T3 is lesser than T2. Then what happens? Because this is at the temperature T2, I can take Q2 amount of heat from that source and convert some W, right, amount of work and reject some Q3 amount of heat into the sink now. Okay. Now, any number of operations, cycles this heat engine does, it always keeps on taking Q2 amount of heat from the sink, which is initially the sink for another heat engine, right? Now that sink is acting like source for this heat engine. So I can extract Q2 amount of heat, no doubt, convert some W amount of work and reject Q3. Now what about this Q3? Q3 is becoming unavailable energy now. Okay, if I want Q3 also to be converted into, I have to find still lower temperature, something like T4 less than T3. Okay, operate another heat engine between T3 and T4. Then the amount of heat rejected into that sink at lower temperature T4 becomes unavailable energy like that. Okay, means anytime, right, whenever what you call a heat engine runs, okay, we are able to take heat from source only. Whatever it is, the heat rejected into the sink always becomes unavailable energy. Okay, now let us extend this. Q1, suppose say T1 is the highest temperature possible in the universe. Okay, I'll keep that as my source. Okay, so I'll keep on extracting heat from that source. Now, T1, T2, T3, T4, T5 like that, lower temperature. Suppose say T0 is the lowest temperature available in the universe. Okay, T0 is lowest temperature available in the universe. So one heat engine runs between T1 and T2. It rejects Q2 into the sink. Another heat engine runs between T2 and T3. That rejects Q3 into the sink. Okay, another heat engine runs between T3 and T4. That rejects Q4 amount of heat into T4 like that. Right, from higher temperature, some heat keeps on getting rejected into lower and lower temperatures. Right, now there is one last heat engine which takes some heat from source, okay, and rejects some Q0 amount of heat into this lowest temperature in the universe called T0. Okay, now that Q0 becomes permanently unavailable in the universe, okay, because that can never be converted into energy. Why? Heat should be converted to energy means we have to have a heat engine. Okay, heat engine always runs between two different temperatures, one lower and higher. This itself is the lowest temperature in the universe. Okay, so I cannot find any further temperature below this T0, means whatever heat that gets rejected into this T0, right, is permanently lost. It becomes unavailable energy. Energy will be there. Energy conservation principle will not be violated. Okay, conservation of energy principle is satisfied here. Only thing is heat is going from useful form to useless form. That's all. Okay, that Q0, right, becomes the unavailable energy in the universe forever. Okay, unavailable energy in the universe forever. That is, right? So its change in entropy, to increase in entropy, ds is equal to, because we are rejecting Q naught into that sink at T naught temperature, its entropy increases. ds is equal to, right, Q naught by T naught, I write. So unavailable energy Q naught equal to T naught into ds. So as any system's entropy ds is increasing, unavailable energy in it is also increasing. This system's entropy is increasing by what amount? Q naught by T naught. Since entropy is increasing, right, whatever heat energy that is going into system becomes unavailable energy. So, right, entropy is related to unavailable energy in the universe. And what is one beautiful consequence of this? Okay, right, we have seen, right, all natural processes in the universe are always irreversible only. In all irreversible processes, right, entropy of the universe keeps on increasing. In all irreversible process, entropy of the universe keeps on increasing. Okay, right, now as entropy of any system increases, unavailable energy keeps on increasing. What does that mean? As entropy of the universe is increasing, unavailable energy in the universe is increasing. Okay, so it means what is happening? Energy is not getting away. Energy conservation principle is still applicable. Remember that. Okay, that cannot be violated, no doubt. But, right, energy is going from useful form to useless form, means which cannot be converted into work. When I cannot convert it into work, heat remains as heat only. It will not go into other forms. Okay, now that is, right, as entropy increases, unavailable energy in the universe increases. Now look at one more consequence, right? This is the highest temperature in the universe, say T1. Okay, this is the lowest temperature in the universe, say T naught. Okay, when you keep on taking heat energy from T1, however, in, right, ideal source it is, its temperature keeps on decreasing. Okay, so, right, when one cycle, two cycle, there won't be any appreciable change in temperature, but continuously for years and years and years together, if you keep on extracting heat from any source, right, as it loses heat energy continuously, its temperature also keeps on decreasing. Similarly, after performing all these heat engines, finally I am rejecting heat into another heat sink at T naught. Okay, when you keep on rejecting heat, when you give a small amount of heat, its temperature may not increase appreciably, but keep on increasing heat into, right, Q naught amount of heat every time into the T naught, what will happen? This one's temperature keeps on increasing. Okay, so highest temperature in the universe, temperature will keep on decreasing. Lowest temperature in the universe, value will keep on increasing. So, okay, what is happening? Highest temperature key is decreasing, lowest temperature is increasing. At some point in the universe, at some time, right, what happens? Right, both this highest temperature source and lowest temperature sink will reach a common equilibrium temperature. Okay, common equilibrium temperature. What is the consequence of that? When entire universe comes to common equilibrium temperature, heat engines will not work. Okay, because heat engines require two different temperatures. Entire universe has come to common temperature. Okay, so what happens, right? Heat engines cannot work. Heat engines cannot work means heat cannot be converted into other forms of energy, but other forms of energy will get converted into heat. All mechanical energy, chemical energy, heat is only produced. Heat is automatically produced by all other forms of energy. When you are charging a capacitor also, the connecting wires will get heated up. Okay, right? The capacitor stores an electrical energy of half QV, right? Half QV energy is lost in the connecting wires. So every time you charge a capacitor, every time you send some current through a resistor to get a magnetic field, means all other forms of energy, right, will keep on getting converted to heat energy, but heat energy will not transform into other forms. Why? Because heat engines cannot work, because entire universe has come to same temperature. What will happen? Entire universe will come to the same temperature. All other forms of energy also slowly keep on getting converted into heat, right? That heat will not transform into any other form. Okay, what happens? Entire energy in the universe will be in the form of heat only, which cannot make any transformation to other forms of energy. That is, we say that universe will die or suffer a heat death, we call. Okay, right, this is called running down of the universe. This is also a scientist called Cuddington has what's called described it as running down of the universe, and this phenomenon is called principle of degradation of energy. Okay, principle of conservation of energy is there. This is different. Okay, principle of degradation of energy. Energy is there, but it is not useful for me. I cannot convert it into any useful form. Okay, so ultimately the ultimate aim of the universe is what? The entire universe will come to same temperature. All other forms of energies also will become transform into heat energy. Okay, universe suffers a heat death. Energy is there, but energy will not go into other forms. Okay, that is known as the running down of the universe, we call. Okay, as a consequence of principle of degradation of energy or running down of the universe suffers a heat death, we call. Means energy will be there, that energy will be in the form of heat. Okay, no other forms of energies will exist, right? So this is the consequence of conservation of what you call the entropy principle. Okay, entropy and unavailable energy, we call. So we should keep in mind, wherever, in whichever systems entropy or surroundings entropy, universe's entropy is increasing. Entropy is increasing means unavailable energy in the system is increasing. Okay, that part of the universe unavailable energy keeps on increasing. Okay, that is one important consequence of this. Okay, next one is, we can frame, the Clausius has framed the second law of thermodynamics in terms of entropy. He said that all natural processes occurring in the universe are, right, irreversible process. In all irreversible process, entropy of the universe keeps on increasing. He has clubbed those two things and has given us one statement for most general statement for second law of thermodynamics. What did he say? All natural processes in the universe will proceed in such a way such that entropy of the universe always increases. Okay, entropy of the universe always increases. Okay, right, this is most fascinating definition for a second law of thermodynamics, right? All natural processes in the universe, will proceed or happen or occur, whatever you can call, will proceed in such a way such that entropy of the universe, such that entropy of the universe increases. Okay, entropy of the universe increase. All natural processes in the universe will proceed in such a way such that entropy of the universe increases. Okay, one statement which far-reaching consequences. Okay, now I can understand, right, why natural things happen in some ways only. Why heat always flows from high temperature to low temperature only. Now I can tell. Okay, why a hot cup of tea becomes cold after 5 minutes or 10 minutes, but never a normal cup of tea will automatically become hot by itself unless you put it on a stove and heat it. Okay, why when I drop this pen or what you call chalk piece or a egg, what you call it, always falls down and breaks into 4 or 5 pieces. Never a broken chalk piece will assemble itself and comes to my hand. Okay, why water always flows from top to bottom only. Okay, like this, all natural phenomena, right? Why things happen in such a way means, right, they all natural process in the universe because they are all irreversible process. Natural processes are all irreversible process. All natural processes in the universe will proceed in such a way such that entropy of the universe increases. Means the ultimate form. Why? Forests only grow in nature. Okay, only when forests grow in nature, right, disorder will increase, entropy of the universe increases. Okay, I cannot maintain a park naturally. Okay, you leave a well-maintained park also for 1 year, it becomes a forest automatically. Okay, right, you drop this pen, you leave this pen, right, it proceeds in such a way such that it drops down and gets damaged, disorder increases. Okay, entropy of the universe increases. So all things in nature, all natural process will proceed in such a way such that entropy of the universe increases. Okay, now I can tell why heat always flows from high temperature to low temperature. Why cannot heat flow from low temperature to high temperature? Though first law of thermodynamics is happy, heat never flows from low temperature to high temperature. Now I can tell confidently, heat must flow from high temperature to low temperature only. Only then the entropy of the universe increases. If reverse case happens, if heat starts flowing from low temperature to high temperature, entropy of the universe decreases, which is not possible according to second law of thermodynamics. Okay, now we can tell Why? Something, what you call, you drop something or something, what you call, slips out of your hand, falls down and breaks. Okay, that is a natural way to happen. Okay, never a broken thing gets assembled by itself unless you are a movie hero, right, and come back to your hand. Okay, if that happens, entropy of the universe decreases, which is not possible. Second law of thermodynamics violates that. Okay, like this. Now if somebody says that some so and so natural thing is happening, right, I will see whether disorder in the universe or entropy of the universe is increasing or decreasing. Okay, natural processes are always irreversible, so entropy cannot remain constant. Only in a reversible process entropy remains constant. No process is reversible. Reversible process is like an ideal gas only. Okay, so all processes are irreversible. In that irreversible process, entropy of the universe must increase. Whether when a so and so quoted process, in that process, whether entropy of the universe is increasing or not, I will say. If it is increasing, I say it is possible. Whether it's really occurring or not, it is possible. If it is decreasing or remains constant, means I can say it is impossible. That process is impossible. It will never happen. Okay, we'll see now, right? Heat always flows from high temperature to low temperature. Only in that way, right, entropy of the universe increases. Now, look here, simply. Now, why heat should always flow from high temperature to low temperature only? Means here there is an object A, there is an object B. Okay, right, this object is at high temperature T1, this object is at low temperature T2, such that T1 is greater than T2. Now say I'll join these two. What will happen? Since A is at higher temperature, say dq amount of heat has flown from A to B. Okay, when dq amount of is flowing out of the system A, this one's entropy decreases. So the change in entropy of A, I'll call it as a ds1. This is nothing but a decrease in entropy is equal to how much, right? dq or delta q by T, I'll write. Delta q by T1, I'll write. Now, what is happening to that delta Q amount of heat? The delta Q amount of heat is going into T2, which is a lower temperature. So, because heat is entering into the system, its temperature, its entropy increases. What is the increase in entropy of system B? D2 is equal to, it is increase in entropy, delta Q by T2. Delta Q by T2. Here entropy has decreased, here entropy has increased. Okay, what is the total change in the entropy of these two systems, that is the entire universe, means ds2 minus ds1 you take. Okay, that is nothing but delta Q by T2, right, minus delta Q by T1. Okay, delta Q by T2 minus delta Q by T1. Okay, T1 is greater than T2. Numerator is same because denominator is more here. This parameter is less. Means the decrease in entropy of A is less. Suppose say that is 10 joule per Kelvin. Increase in entropy of system B is more because T2 is smaller number, delta numerator is same, delta Q by T2 is less. Okay, if this delta Q by T1 is 10 joule per Kelvin, delta Q by T2 will be more than 10 joule per Kelvin. Let us call it as 12 joule per Kelvin. Means in the universe what happened? At one point in the universe, entropy has decreased by 10 joule per Kelvin. In another part of the universe, entropy has increased by 12 joule per Kelvin in that process. Okay, due to that process. So, decrease is 10 joule per Kelvin, increase is 12 joule per Kelvin. That is, net amount of increase in the entropy is 2 joule per Kelvin. 2 joule per Kelvin. Okay, because entropy of the universe is increasing, this process is possible. By chance, what happens if heat flows from lower temperature to higher temperature on its own? Okay, right? Delta Q by T2 is, this is lower temperature, right? Delta Q by T2 is less. Okay, delta Q by T1 is more. Okay, so delta Q by T1 minus delta Q by T2, if I take that, it will be negative. Means entropy of the universe decreases. Entropy of the universe can never decrease according to Clausius statement of second law. Entropy of the universe will keep on increasing. All natural process in the nature must proceed in such a way such that entropy of the universe should always increase. Okay, means here, if heat flows from high temperature to low temperature, delta Q by T1 minus delta Q by T2 will be negative. That is, entropy of the universe decreases, which is impossible. If heat flows from high temperature to low temperature, delta Q by T2 minus delta Q by T1, that is positive. That is, entropy will increase. So, heat should always flows from, or heat always flows from high temperature to low temperature only. Okay, never heat can flow in reverse manner. That's why the other statement of Clausius statement in terms of refrigerator also we can understand. What is the function of refrigerator? Refrigerator has to take out heat from a low temperature object and transform that, or what you call, send it to a high temperature source. Okay, this is a refrigerator. What is the function of a refrigerator? It has to take out some heat from a low temperature sink, Q2 amount of heat. It has to take from a low temperature sink T2, and it has to reject that heat into a higher temperature. That's the function of a refrigerator. Whatever things you are putting inside the refrigerator should become cold. Okay, right? They should get cooled. Means what should happen? Someone has to take out heat from that. And what will happen to that heat? That heat should be thrown into the atmosphere. Means inside, whatever you are keeping inside the refrigerator is at lower temperature. Atmosphere is at higher temperature. Heat is getting transferred from low temperature to high temperature. On its own, it is impossible. Okay. No refrigerator cannot take some heat from a low temperature sink and transform it into, right, or send it into a high temperature source T1 without the aid of external work. This is Clausius statement of second law of thermodynamics in terms of refrigerator. Okay, unless I do some external work, no refrigerator can transfer heat from a low temperature object to a high temperature object. Without this, if refrigerator transforms heat from low temperature to high temperature, transfers heat, what will happen? Heat is flowing from low temperature to high temperature, which is against the second law of thermodynamics principle. Okay, now I can understand why I need an external W. Okay, that external W will save us from the violation of second law of thermodynamics. Unless we have W, right? If you don't put this W, what will happen? Heat is going from low temperature to high temperature, which is a violation of second law of thermodynamics. Okay, right? So we can understand Kelvin-Planck statement also. Okay, we can understand Clausius statement in terms of all other statements can be understood from the point of view of this entropy statement of Clausius, second law given by Clausius. Okay, now we'll see what is another form of entropy. That is, entropy is related to disorder existing in the system. The system's entropy is more means I'll understand disorder in that system is more. This system's entropy is less means I can understand disorder in this system is less. Okay, now we'll see that what will happen. How? You take a system like this. Okay, a vessel is there, some chamber. I'll split one container into two chambers like this, separated by a stopcock. I'll put gas molecules in one chamber only. In other chamber, right, there is vacuum, no gas at all. Okay, gas is present only in one chamber. Okay, these molecules you have seen. Kinetic theory of gases says what? Gases contain molecules, atoms are molecules which are moving randomly. Okay, random direction, colliding with themselves, colliding with the walls of the containers. Okay, haphazard, right? Zigzag manner molecules will moving here and there. There is some disorder. Okay, but I want to search for one specific molecule, say. Okay, if I want to search for any specific molecule, what should I do? I have to, because this molecule keeps on changing its position, path, all continuously. But whatever it is, if I search this much volume of the vessel, it is sufficient. This molecule will be present somewhere. If not here, it may keep on moving from here to here. But when I carefully search the entire volume V, I can find this molecule. I can find this. There is disorder, no doubt, but there is some, disorder is there. Right, I have to put some effort to locate one specific molecule. Okay, but that effort is confined only to searching in this volume only. Now, if I remove this stopcock, what will happen? Okay, because there is vacuum here, pressure is zero, this gas rushes into the second chamber. When I remove the stopcock, all the gas molecules will try to diffuse into this region. Okay, rush into the second region. Right, some molecules will come to this side also, such that pressure of the gas is uniform throughout. Okay, part of the gas will come to this second chamber also. Right, now that molecule also maybe here might have come to this chamber, we don't know. Now the gas is covering the entire 2V volume, let us say. Okay, total volume is 2V. Okay, Now, what is happening? If I want to search for the same molecule, what is happening? Disorder of the system has increased, I will say. Why? Now, if I simply search for V volume, it is not sufficient. I have to search 2V volume, means my efforts will increase now. My efforts will increase now. Okay, because that whatever is that disorder is, earlier it was confined only to a volume V. Now the disorder got extended to 2V volume. Okay, so what happened to the disorder of the system? Disorder of the system has increased. And what type of process it is? It is a natural process. It is an irreversible process. Okay, gas rushing from high pressure region to low pressure region, right? It is an irreversible process. Okay, so in an irreversible process, even if this system is an isolated system, okay, even if the system is an isolated system, okay, because the process is an irreversible process, what should happen to entropy? Entropy of the universe should increase. Entropy of the isolated system is increasing, means entropy of the universe is increasing automatically. Okay, right? Entropy of the universe is increasing, right? Disorder also is increasing. Okay, so wherever disorder is increasing, we can say that its entropy is increasing, or vice versa. Okay, wherever disorder is increasing, I can say entropy is increasing, or entropy is increasing, disorder is increasing. Okay, same earlier also in Carnot engine. Source is at high temperature. Okay, source is at high temperature means what you call a system which is at high temperature, the molecular thermal agitation will be more. Molecules will be vibrating more and more violently. Let this source be some sample of iron which is at high temperature, say 1000 degrees Celsius. Iron is at 1000 degrees Celsius, that is acting like my source. Okay, what will happen? Because the temperature is very high, right? In the beginning of what you call gases, we will see macroscopic property called temperature is microscopically due to the kinetic energy of atoms or molecules. In the case of gases and liquids, it is kinetic energy of molecules. In the case of solids, in a solid, atoms cannot move. They are fixed to their respective crystal lattice positions, isn't it? But, right, what will happen? No atom above absolute zero will be at complete rest. The atoms will be vibrating about their equilibrium position here and there randomly. Okay, that is known as thermal agitation. Okay, this three-dimensional vibration about their, right, equilibrium position of atoms or molecules is called thermal agitation. In the case, once we go to solid state physics, we'll call it as lattice vibrations. Okay, right? Now, these thermal agitation will keep on increasing as temperature keeps on increasing. Okay, right? When keep on increasing temperature, atoms will start vibrating with more and more amplitude, more and more violently. Thermal agitation keeps on increasing. More disorder. Okay, you take the same iron sample to be at 0 degrees Celsius. 0 degrees Celsius means, okay, right, here the amplitude of vibration of molecules will be less. Okay, molecules will be vibrating with smaller amplitude and lesser frequency. I'll say disorder of molecules or thermal agitation of molecules is smaller here. Okay, thermal agitation is small means disorder in the system also is less. Disorder in the system is also less. As I keep on increasing its temperature from 0 degrees Celsius to say 100, 200, 300 till 1000 degrees Celsius, what will happen when I keep on heating, right? Molecules will absorb this heat energy and start vibrating more and more violently. Right? So what is the meaning here? As temperature increases, thermal agitation is increasing, disorder of the system is increasing. Okay, right? Now, the source is at 1000 degrees Celsius means molecular disorder is more. Okay, entropy is more. Similarly, a sink, let us say sink is nothing but iron sample only at 0 degrees Celsius. Here, atoms are having lesser amplitude, lesser frequency, thermal agitation is less, disorder is less. So, in a sink, naturally, disorder will be less. In a source, naturally, right, because it is higher temperature, disorder is more. When you are, when you take some Q1 amount of heat, okay, right, convert some W amount of work and reject some Q2 amount of heat into a sink at lower temperature, what is happening here? When you are taking out heat, system's entropy is decreasing. Because you are taking out heat, temperature of the source keeps on decreasing, thermal agitation keeps on decreasing, disorder in the system source decreases. Okay, you are doing some W amount of work, system goes back to its initial states as the system's entropy remains constant, heat engine's entropy remains constant, no doubt, but you are rejecting Q2 amount of heat into a sink at lower temperature. When these molecules gain that Q2 amount of heat, their thermal agitation increases, their disorder increases. We say that because heat is getting rejected into the sink, sink's entropy increases by what amount? Q2 by T2. As sink's entropy is increasing, disorder of molecules also increasing because thermal thermal agitation is increasing. Okay, so wherever entropy is increasing, disorder in the system is increasing. Wherever entropy is decreasing, disorder in the system is decreasing. So entropy is a measure of degree of disorder. Okay, from all these things we can say that entropy can be understood in terms of disorder also. Okay, whichever system's entropy is more, disorder is more. Whichever system's entropy is less, disorder is less. Okay, right? These are the best examples to say that wherever entropy is increasing, it is associated with more disorder. Wherever entropy is decreasing, it is associated with, right, decrease in disorder. Okay, when a metal becomes a superconductor, its entropy decreases abruptly, we say. That's why superconducting state is a more orderly state of affairs, we say. In superconductivity also, right, when mercury transforms from normal conducting state at 4.12 Kelvin, right, mercury suddenly becomes a superconductor. So below 4.12 Kelvin, it behaves like a superconductor, right? Temperature is decreasing, mercury's temperature keep on decreasing from 10 Kelvin onwards. Its entropy also keeps on decreasing. But suddenly at 4.12 or 16 Kelvin, what will happen? Transforms into superconductor. Okay, right? Just because it transformed into superconductor, there will be some sudden drop in entropy. Okay, so that sudden drop in entropy implies that superconducting state is a more orderly state of affairs. Okay, how do we later on understand it? Normal free electrons, right, transform themselves into Cooper pairs. Some order is increasing. Instead of moving individually, electrons will pair up and start moving. Okay, such that disorder decreases, we say. Superconducting state is a more orderly state, we say. Okay, so this is the entropy disorder explanation. Okay, right, now we'll see some calculations of entropy changes in some systems. What happens when you heat a gas? What happens when you heat a liquid? Okay, how much is the increase in entropy? Right, we say change in entropy calculations, we call that. We'll cover in the next video. Thank you.